Alright. How's everybody doing? Going to cover section 1.2, which is an introduction to what are called it's an introduction to what are called initial value problems. Okay. We're going to talk about first and second order initial value problems. I guess you could talk about third order, fourth order, and so on. And in general, you could talk about nth order initial value problems. Okay, so first of all, I'll probably just show you what a first order and second order looks like, and then I'll generalize that. Okay, so at the top, what a first order initial value problem would be to solve a first order differential equation, and this is what I would refer to as the normal form. Okay, so when you have the first derivative in terms of a function of x and y, okay, that would be a first order differential equation. So dy dx, or y prime, that's the highest order derivative that appears. And then the right hand side of the differential equation would just be some function of x and y. Okay, and again, if you solve that, we haven't really seen how to solve these yet. In the first section, y'all would have been given a differential equation, and then you were just given either a particular solution, which does not depend on a constant, or you were given what was called family of solution that would depend on some number of constants. First order differential equation, the general solution, as I would call it, or the family of solutions, would obtain a single constant. Okay, so for a first order differential equation, okay, you would solve that differential equation, find a function y in terms of, in this case, a single function c, but then you would solve this differential equation subject to an initial condition. So this is where you would know a value of the function. Okay, and that allows you to solve for the arbitrary constant and get what's called a particular solution. You can talk about second order diffeqs, or second order DEs, and again, this is in normal form. You could have the second derivative as a function or in terms of x, y, and y prime. But in this case, since it's second order, when you solve this differential equation, you're going to find a function y, and generally you're going to find this function y in terms of two arbitrary constants. Okay, so you would need two conditions to determine those constants. So you need a value of the function y and a value of its derivative. Okay. Now hopefully you're starting to see the pattern. A second order differential equation, to find a particular solution, you would need to know two initial conditions. Okay, a value of the function y itself and a value of y prime. Okay, so in general, when you're solving an nth order differential equation, okay, in normal form, the nth derivative would be in terms of x, y, y prime, all the way up to the n minus first derivative, and then you would actually need n conditions. Okay, so notice nth order differential equation, you would need n conditions. You need a initial value for y, an initial value for y prime, that would eliminate a second constant. This would be the nth condition. This is just saying that you know the value of the n minus first derivative at a value x of n minus 1. Okay. So basically, again, nth order differential equation, you'd have n initial conditions. Okay. So, example 1, say you were given that a family of solutions to the DE, so the family of solutions y would equal negative 1 over 2x squared plus c. So that's that. C is c is that arbitrary constant that would appear after you solve the first order differential equation right here. Okay, so it turns out that if that is a function y, if we're given this function y, so y, its derivatives, and x are all related in this way. Okay, so it's a first order differential equation. We have the family of solutions. It says solve the initial value problem given the condition y of 0 equals 1/8, and it says give the domain of the solution or interval of solution as well. Okay, so again, notice this is a first order differential equation. Okay, the highest derivative that appears is y prime. Okay, if you wanted to write that in normal form, right now it's in what's called the general form. Okay, you could write that as y prime equals 4xy squared. We'll actually learn how to solve this differential equation eventually. This is what is called a separable differential equation, and it's probably the type of differential equation we will learn how to solve first. Okay. Now, when you solve for that, you're going to get a family of solutions with one arbitrary constant because it's a first order differential equation, and then you also have an initial condition to eliminate the parameter. So now I'm going to do that first. So I know that y of 0 equals 1/8 has to also equal negative 1 over 2 times 0 squared plus c. Okay. Alright, so I plugged 0 into my solution, my family of solutions, and I set that equal to negative 1/8. Sorry, I set that equal to 1/8. Now what this tells me then is 1/8 is equal to minus 1 over c, and it can be shown that c would have to be minus 8. Okay, so y equals minus 1 over 2x squared minus 8 is the particular solution. Okay, subject to the condition y of 0 equals 1/8. Okay. You can again verify that that is a solution of the differential equation by taking the derivative and then plugging y prime x and replacing y as well, and you will see that if you plug that all into the left hand side and work it out, you will get 0. Now it says give an interval or domain of solution. Again, there's a million names for this, but I think that I usually like to talk about domain of the solution or interval of the solution. Okay, so I'm going to come over here. Now, whatever your interval is, okay, I'm going to keep my initial condition highlighted over here. Or maybe what I'll do is I'll box it. My initial condition happens at x equals 0. So whatever interval, I'm going to choose the largest interval for which my solution and its derivatives are continuous that also contains x equals 0. Okay, so now you'd probably have to go ahead and find y prime. Okay, so y prime is equal to, using the quotient rule, I believe that y prime is 4x over 2x squared minus 8. So the domain of the original function plus its derivative is the same, and we know that functions of this form are continuous on their domains. Now if you look at the denominator factors as 2 times x minus 2 times x plus 2, and I guess you could think about the domain of y or y prime the domain of just those as functions, the only one that contains 0, and what I'm going to choose for my interval of solution, is going to be minus 2 to 2. Okay. So if I know my family of solutions and I know an initial condition, I can solve the initial value problem by finding the arbitrary parameter c and then finding the largest interval for which the solution and its derivative is continuous that also contains x equals 0. Okay. Alright, so again, there's the solution of the differential equation, and there's the domain or interval of solution at the bottom left. Okay. Okay, so we just did a first order initial value problem. The family of solutions had one parameter. We needed one initial condition to eliminate that parameter. And then the interval of solution has to contain the x coordinate of your initial condition. Okay. You find the largest such interval containing that value for which the solution, its derivatives, and the differential equation are all defined. Okay, so second order initial value problem is going to involve two arbitrary constants in the family of solutions. You're going to need two initial conditions to solve this. Okay, so the family of solutions, I'll write that down, is c sub 1 cosine, oh man, Mark. The family of solutions is x equals c sub 1 cosine 2t plus c sub 2 sine 2t. Okay, this is the family of solutions. And then, so once we learn a method for solving differential equations, there's going to be kind of two types, like just like when you integrate, you can integrate a function to find the family of antiderivatives, or given certain conditions, you can find the particular antiderivative. And the first thing you're always going to do, you would find the antiderivative regardless before you find the constant of integration. So same thing here, when we solve differential equations, you're going to find the family of solutions first and then need conditions to find those constants. And when we get there, we'll actually learn the method for finding the family of solutions. So here we're just assuming we have that. And here's my two conditions. Okay, so I'm going to find C1 and C sub 2 by plugging those conditions. I have to plug something into the original function and the first derivative. So now I have to find x prime, and x prime is going to be, okay, there is the first derivative, x prime, negative 2c1 sine 2t plus 2c2 cosine 2t. And now what I'm going to do is I'm going to just plug my initial conditions into the original and to the derivative. So x of pi over 2 equals 2. Okay, now I can plug pi over 2 into the first equation. Okay, you can check this on your own, but you're going to get... Okay, so we know that x of pi over 2 equals 2. And that has to be the same as what you obtain when you plug pi over 2 into the family of solutions. You'll get c sub 1 cosine pi plus c sub 2 sine pi, and I believe that's just minus c sub 1. Okay, right? Cosine pi is negative 1, sine pi is 0. So what that tells me then is that c sub 1 has to equal, and I'm going to write this up here on the right, c sub 1 has to be negative 2. Okay, now what I'm going to do, I know that c sub 1 is negative 2, so you can use that now when you use your second condition and plug that into the first derivative. Okay, so you know that x prime of pi over 2 is equal to negative 4, but I now know that that has to equal, so c sub 1 right here, I'm going to find this first. C sub 1 is negative 2, so I get 4 sine of pi plus 2c sub 2 cosine pi. Okay, sine of pi is 0, so that part drops off. And cosine of pi is negative 1. So I know negative 4 is equal to negative 2c sub 2. So c sub 2 is going to equal positive 2. Let me write that up here. Okay. So that means that the particular solution, or the solution to the initial value problem, would be x equals negative 2 cosine 2t plus 2 sine 2t. And then your interval of solution, notice that x, its derivative, and the original differential equation are defined for all real numbers. And you have to, your solution can be any interval containing pi over 2, where your solution and its derivatives are continuous and the differential equation is defined. So in this case, you could choose all real numbers to be the domain or interval of solution. Okay, so there would be the particular solution and the interval of solution. And I should also say that you could check that you can either check that the particular solution is a solution, or you can check that the arbitrary family of solutions is indeed a solution by, you'd have to take the up to the second derivative, since this is second order, and then you would plug x double prime and x into the left side of the differential equation. Okay, and when you do that and simplify, you should get 0. Okay. Okay, so now what we're going to do is, so we've seen a few things. We hopefully know the difference now between a particular solution and a family of solutions. Any solution of a differential equation has to satisfy the differential equation, meaning itself and its derivatives, when substituted into the differential equation, either lead to an identity, or if it's an implicit solution, you could use implicit differentiation and solve for the highest derivative that you're looking for. And you can use repeated implicit differentiation if necessary. So now, when does a solution exist? And it does turn out that if a solution exists, it is unique. And I want to maybe read this first and then draw you a picture to help you understand this. So I want you to think about the xy plane for a second. Okay. So you usually think of, in this first one, I want you to think of the first sentence there. Just picture this in your mind. So you'd have a rectangular region in the xy plane, and this would be like a, if you think about linear algebra, this would be a rectangle that contains all the points inside plus the interior. So on the x-axis you go from A to B inclusive, and on the y-axis you go from C to D inclusive. Now, that rectangle is going to contain a point, x0, y0, in its interior, and the idea is you want to think of this point right here as the point that results from your initial condition. Okay, or certainly x0 is going to be the value that's used in almost all of your initial conditions or your initial values. Okay, now I want to talk about this whole partial f, partial y thing right here. So compare that to the differential equation over here. So the initial value problem, that would be a first order differential equation, and then having a condition right here. Notice that the initial condition is y of x0 is y0. Now, if you look at the differential equation, I want you guys to focus down here on this, but more specifically focus on the function in terms of x and y on the right, and think of that as a function of two variables, like Calc 3, Calc 4. Okay, so let me clear this off for a second. Let me come up to this again. So so if that function, if dy dx, which is a function of x and y, f of xy, if that and its partial derivative with respect to y are continuous in that rectangle, you should always be able to find an interval, okay, this part right here. This is just saying it's some interval containing x naught, okay, that's the x coordinate of your initial condition, okay, and it's going to be completely contained on the x, within the x coordinates of that rectangle. So it's in the interval, closed interval from a to b, and a unique function y of x defined on that interval. That's a solution of the initial value problem. Okay, and the interval I of definition for this initial value problem, if you read at the bottom, okay, it's usually taken to be the largest interval that contains x naught over which the solution y of x is defined and differentiable. Okay, this is essentially what I've been doing before. I've been looking at y and y prime, and I want to know, right, differentiable, that's the domain of the derivative, and you're also making sure that that interval is also contained in the domain of the solution y. So again, basically, your intervals of solutions are just the largest domains of y and its derivatives that contain x naught, the interval, or contains the x value of your initial condition. So if you want to think of this in terms of a picture, you would have your differential equation, your first order differential equation, dy dx, could always be found in terms or written as a function of x and y. Okay, and then again, you have some initial condition. So when you find the solution y, we know this initial condition, y of x naught equals y naught. Now, if I think of the solution curve, so if I found y of x, I don't know, we don't necessarily know what the solution function looks like, but say that's the solution curve for this particular solution. And on the graph, right here, that's the point x naught, y naught. Okay. And what's happening is, okay, what if you have some rectangle like this? You've got some rectangle containing that point, and all you need to know is that f of xy and dy dx, or sorry, let me go back, partial f and with respect to y, so you take the partial derivative with respect to y, are continuous as functions of two variables on this rectangle R. Okay, so this rectangle up here is R. Okay, then this is just saying that a particular solution of the initial value problem or the differential equation will exist, and it's the largest interval, contained in that AB. So your interval I is going to be somewhere down here. So if you look at the x-axis in my graph, there's going to be some interval I0 or I naught. Okay, and x naught's going to be contained right there. So there's some interval I sub 0 containing x sub 0 on which a particular solution exists. It's unique, and again, the interval of solution is the largest interval containing x naught, so that basically all of the function y and all its derivatives are defined on that interval. and contain x naught. Okay, so that's all it needs to happen when you're finding the interval of solution. Alright, so example 3, here's an initial value problem. It's a first order differential equation. To solve the initial value problem, since it's first order, you need one initial condition. I know the solution curve has to contain the point 0, 4, or in other words, y of 0 equals 4. Does theorem 1.2.1 guarantee the existence of a unique solution? Okay, what about the initial value problem? Dy dx equals y to the 2/3 with the condition that the origin has to be contained on the solution curve. Okay, so let me call this, I'm going to call this initial value problem 1, and that's initial value problem 2. Now, again, we don't know how to find the solutions yet. Okay, all we're really doing right now is talking about what solutions are, the types of differential equations we're solving, like, you know, first order, second order. Are we just finding the family of solutions, like an indefinite integral, or are we finding a particular solution after being given some initial conditions? So what I'm basically doing right now is, does that theorem tell me that both of these initial value problems have a unique solution? Okay. Is it guaranteed? Okay. So number 1, I'm going to put that right now into standard form, or sorry, normal form. And you would solve for y prime, you're going to get x squared over 4 minus y squared. Okay. And notice I'm looking at y of 0 equals 4. Now, this function on the right is what the previous theorem referred to as f of xy. And now you can take the partial derivative with respect to y. Okay, so you take the partial derivative of f, again that's just the right-hand side of the differential equation up here. And we're gonna find where that and its partial derivative with respect to y are continuous. And I believe that partial f partial y should be 2x squared y over 4 minus y squared quantity squared. Okay, so now I'm going to draw the xy plane for you. Actually, let me be a little smarter about this. My initial condition up here is y of 0 equals 4. So, I think I can draw this more like that. There we go. That's the x-axis, that's the y-axis. Here's, if I go up 4 units, here's the point 0, 4. Okay. Now, you'll notice that the only rectangle for which f of xy and partial f partial y are defined, or continuous, okay, is going to be from y equals -2 to 2, and there's no restriction on the x-coordinate, so you're only looking at the denominator. So I'm going to draw a couple strips here. The rectangle can actually be infinite. 6, 7, there's another rectangle up there. Okay. So 6. Actually, hold on, I've got to fix this for a second. Okay, so, sorry, refer to the graph in the upper right corner of the screen. Okay, so I've got the y-axis and the x-axis. So actually, if you look at f of xy or partial f partial y, those are actually defined everywhere in R2 except for y equals 2 and y equals -2. Okay, so when I'm talking about that rectangle in the previous theorem, it's actually up here. Okay, and again, it can be, I guess it's any rectangle that's inside of that whole part of the xy plane. Okay, and again, since f of xy and partial f partial y are, you know, here's one such rectangle I could draw, right? Okay, there's a rectangle on a piece of R2 where f of xy and partial f partial y are, I guess, continuous, which is on their domains. Okay, and notice my my initial condition, y of 0 equals 4. Okay, that is fully contained in a region of R2 where f of xy and partial f partial y, those are both continuous. Okay, that's where they're defined. And any rectangle around that, I could basically guarantee a solution to the initial value problem. I guess you could probably make the interval of solution as large as you want, since the there's no restrictions on x on f of xy partial f partial y or the original differential equation. Okay, so the answer there, long-winded answer, is yes for the first differential equation. Theorem 1.2.1 guarantees the existence of a unique solution. Okay. And another thing I should mention for this first initial value problem right here, again, you would take the interval of solution to be the largest interval that contains 0 on which y and y prime are defined. And I guess the original differential equation is defined as well, which is, again, it's essentially just where y and y prime are defined. Okay, and if I had we don't actually have the solution in front of us, so we can't really know, I guess, which interval to take 100%. Okay, now for the next one, okay, this time f of xy, this is for number 2, f of xy is y to the 2/3, and partial f partial y would be 2/3 y to the negative 1/3. Okay, so we're just taking the derivative with respect to y using the power rule. Okay, this is equal to 2 over the cube root of y cubed. Okay, so f and partial y are basically both simultaneously defined and continuous everywhere except for where y is equal to 0, which would be the x-axis. Okay, so I draw this picture now. Here's the point 0, 0. Okay. I want to remind you again that f and, again, here's the y-axis, here's the x-axis. F, okay, again, that's just the right-hand side of the first-order differential equation in normal form. That function and its derivative with respect to y are defined everywhere except on the x-axis. But the problem is the point of, look at the point given, 0, 0, that's my initial condition. That point is not contained in a rectangle on which, so notice 0, 0 is not contained in a rectangle. Okay. And I can't write this next part because I'm out of room, but hear me. 0, 0, the point coming from your initial condition, that needs to be contained in a rectangle. And inside that rectangle, f and partial f partial y need to be continuous. Okay, or i.e. in this case defined. Okay, so for the second IVP, Theorem 1.21 does not guarantee the existence of a unique solution. In the first case, right, the initial condition was the point 0.04, and we were able to find a rectangle on which f and partial f partial y were continuous. Okay, but that is not the case for the second differential equation. I don't want to go into that in too much detail. If you have any questions, I can check your work. We can do a Zoom meeting together. We're going to meet on Thursday. Get a hold of me if you need anything, but I'm going to stop there. Have a good one. Thank you.